In this video, I'm going to talk about when does the derivative not exist. So remember that the derivative is the slope of the tangent line, but more importantly, it's the limit of the average rate of change. And we've talked about a bunch of times the limits aren't going to exist. So since limits can exist, it's possible for the derivative to not exist. All right, here's just a general fact. I'm not going to prove it for you because it's kind of actually difficult to prove. But if f of x is a function, and that a be in its domain, so a is a value you can plug in. Right? If we can find the derivative at a, then f is continuous at a. So if we can take the derivative, then the function has to be continuous. And the what's called the contrapositive, this is the important part that I want you to know. If f is not continuous, then it's not differentiable. So automatically we have one place where the limits, the derivative is not going to exist. If we don't have a continuous function, then the limit and the function value don't make sense together. So we can't do that limit definition of the derivative. So the derivative is not going to exist. So if it's not continuous, you can't find the derivative. All right, next we're going to look at the absolute value function. All right, so the absolute value function looks like this. If I can actually draw, it's kind of just a v. And what's the derivative going to be at 0? All right. Well, we know the derivative is the slopes of the secant lines. All right, so the limit of the slope of the secant line. So I could do limits on the left, and I get all these secant lines. So everything to the left of 0 for this derivative limit would say that my derivative is going to be -1, right? It's the slope of that line to the left. And to the right of 0, everything's going up this direction. That would say that the limit to the right of 0, when I'm trying to find f prime of x, would be 1. Right. And this is exactly what we don't want to happen. Everything to the left over here, my derivative is going to be -1. Everything to the right, my derivative is going to be +1. And there's this kind of jump that happens right at 0 where my limits, my derivative is not going to exist. Right. And the kind of property that's causing this is whenever you have a sharp corner, right, these tangent lines are kind of opposite from each other and they don't agree, so they're not going to have a derivative. So these are called cusps. All right, just think about it as corners. All right, whenever you have a corner on a graph, a sharp corner, whether they look like this or like that or like that, any sharp corner, the derivative is not going to exist because we have these two competing tangent lines. All right, now we have y equals the cube root of x. So let's look what the graph looks like. All right, the graph of y equals the cube root of x looks like this. I want to see at x equals 0, what is the derivative going to be? All right, well, if you follow this along, what's happening right at 0 for the cube root of x? It's going straight up before it does this turn back. So the tangent line is this straight line up and down. And what's the slope of a line that's straight up and down? Y equals, m equals y2 minus y1 over x2 minus x1. But if I'm on this vertical line and I take 2 points, the x values are the same. It's going to be 0 on the bottom of the slope equation, which means this is a slope that does not exist. And if the slope of the tangent line doesn't exist, that's the same as the derivative. The derivative does not exist. All right, so these are called vertical tangent lines. I even draw it a little bit better. It's kind of like when your graph looks like this. It goes straight up for a second and then goes across. All right, so this vertical tangent line, when your graph is basically going straight up and down, your derivative's not going to exist. So if we consider this function, when will the derivative not exist? All right, so we have 3 different times. All right, one is continuity. All right, if our function is not continuous, it can't be differentiable. The second was a cusp. And the third was a vertical tangent. So we just have to find those things. So first, continuity. We know continuity, we learned it before. It's all the places you'd have to lift up your pencil, all right, all the gaps and stuff in your function. So we have one discontinuity at -1. We have another discontinuity at 0. And another discontinuity at 1. All right, so x equals -1, 0, and 1. The derivative will not exist, all because it's not continuous at those places. Okay. And there's just one other place where this derivative won't exist, and that's at the cusp. And right here, you can see this really sharp corner of my graph. All right, if it looked like this, a nice smooth curve, it'd be fine, but a sharp corner at x equals 2 means the derivative does not exist. All right, so a quick rundown of the things. All right, there's 3 places the derivative is not going to exist. When a function is not continuous, at a cusp or a sharp corner, and at a horizontal tangent, vertical tangent. Because the straight up and down line is what's bad. Horizontal tangents are actually fine, and they'll actually be really important in the future. All right, so it's a vertical tangent is when the derivative will not exist.